Hi, my name is Professor James. Welcome to this journey through space. Today we are going to study the chapter, which is CAD and 3D modeling for aerospace structures. In this chapter, we'll explore how computer-aided design, CAD, and 3D modeling are transforming aerospace engineering by providing digital tools to design, simulate, and optimize complex structures. These tools are integral in creating everything from aircraft wings and fuselage to engine nacelles and control surfaces, helping engineers test their designs virtually before physical production. Let's dive into how these tools work, the process behind them, and the impact they have on aerospace design and manufacturing. So, CAD foundations and software. CAD tools are the backbone of modern aerospace design. CATIA, Fusion 360, Siemens NX, and SolidWorks are some of the most widely used CAD software in aerospace. CATIA is dominant in large aircraft manufacturing, used by companies like Airbus and Boeing for creating detailed 3D models of aircraft. Fusion 360 is more accessible and is often used in academic settings and by smaller startups for lightweight designs. These software packages provide specialized aerospace workbenches, offering templates and features tailored to designing complex aerospace components like wings, fuselages, and propulsion systems. Mastering these tools is essential for any aerospace engineer, as they integrate key features such as aerodynamics, structural integrity, and system integration into the design process. Component modeling. Modeling individual components is the first step toward designing a complete aerospace structure. Airfoil profiles are created using parametric data, often importing coordinates from aerodynamic databases such as NACA to ensure accurate shape generation. For fuselage design, station profiles at various cross-sections define the complex curved surfaces of the aircraft body. Control surfaces like rudders, elevators, and ailerons are modeled by applying specific geometric constraints to ensure proper deflection and aerodynamic performance. Each component is carefully modeled with attention to detail, from wing spars to engine nacelles, ensuring that every part fits together seamlessly in the final assembly. Parametric constraints are used throughout the modeling process to maintain dimensional accuracy and ensure that all components meet the necessary design specifications. Assembly and simulation. Once individual components are modeled, the next step is to integrate them into a complete assembly. Assembly constraints like mate, align, and parallel ensure proper alignment and fitting between parts such as wings, fuselage, and engines. Kinematic studies simulate the movement of control surfaces, landing gear deployment, and other moving parts to ensure that they function as intended. Simulation is key to identifying potential issues in the assembly, such as interference between parts, ensuring that the design works under real-world conditions. Integration tools in CAD software help visualize how different components fit together and check for mechanical conflicts or aerodynamic inefficiencies. Proper preparation for analysis is crucial, as assemblies must be ready for structural and aerodynamic simulations to validate the design's performance. Advanced 3D modeling techniques. To create complex aerospace structures, advanced 3D modeling techniques are used. Extrusion, revolution, and sweep operations are basic 3D modeling techniques that form the foundation for creating intricate geometries. Lofting is used to transition between multiple profiles, such as for the fuselage, allowing the creation of smooth aerodynamic surfaces. Boolean operations, like union, subtraction, and intersection, are applied to combine or subtract shapes, useful in designing engine nacelles, wing slots, and control surfaces. These operations are combined to model everything from simple components like brackets to more complex systems like turbine components. Mastery of these techniques enables aerospace engineers to create efficient, complex designs that meet both aerodynamic and structural requirements. Airfoil design and implementation. The design of airfoils is crucial for optimizing aerodynamic performance in aircraft. Airfoil profiles are typically based on NACA coordinates, and designers often import aerodynamic data to create accurate profiles that meet specific performance goals. Proper scaling and chord length adjustment are necessary to achieve desired lift and drag characteristics. Leading and trailing edges must be refined to ensure smooth airflow, which is critical for reducing turbulence and improving fuel efficiency. Twist and incidence angles are applied parametrically to optimize the airfoil's performance across the entire wingspan. The precise implementation of airfoil shapes is key to achieving the necessary aerodynamic performance, and small changes in airfoil design can significantly impact the flight dynamics. Fuselage and nozzle, modeling. The fuselage and engine nozzles requires careful consideration of both aerodynamic performance and structural integrity. The fuselage is typically created using lofting operations between station cross-sections, ensuring smooth aerodynamic surfaces that reduce drag. Structural components, such as frames and stringers, are added using reference planes to support the fuselage's structural integrity. Cockpit and windscreen modeling involves creating complex curved transparent surfaces, integrating structural frames, and ensuring visibility requirements for pilots. Engine nacelles and pylons are modeled with internal flow paths to optimize airflow and reduce drag. Propulsion nozzles require careful design to ensure that the flow paths align with engine requirements, incorporating thermal expansion allowances and cooling provisions. Assembly techniques and constraints. In large aerospace projects, assembly techniques play a key role in ensuring that components fit together correctly. Assembly constraints like mate, align, and tangent ensure that parts, such as the fuselage and wings, are properly aligned to prevent issues in the final assembly. For control surfaces, constraints are applied to ensure that components, such as ailerons and elevators, move without interference. Distance and angle constraints are applied to ensure proper positioning of control surfaces and landing gear, which are critical for flight performance. Managing these constraints in complex assemblies helps prevent over-constraining, ensuring parts move as intended in real-world applications. Proper assembly is crucial for both aesthetic and functional reasons, ensuring that the aircraft performs well and meets both engineering and regulatory standards. Reverse engineering techniques. In some cases, existing parts need to be digitally captured and modified, a process known as reverse engineering. 3D scanning technologies, such as laser scanning, structured light, and photogrammetry, are used to capture physical components and convert them into digital models. These models are then processed and refined to create accurate 3D representations, eliminating noise and discrepancies. Surface reconstruction techniques are used to convert point clouds into smooth, manufacturable surfaces. Feature recognition helps convert scanned data into usable CAD models, identifying critical features like holes, edges, and fillets. Reverse engineering is essential when original designs are unavailable, and it helps create replacement parts or improve existing designs. CAD for manufacturing documentation. Once the design is complete, detailed manufacturing documentation is required to ensure that the design can be built correctly. Bill of Materials, BOM, lists all the parts needed to assemble the structure, including material specifications and quantities. Technical drawings use geometric dimensioning and tolerancing, GD&T, to define the part's specifications, ensuring accuracy in manufacturing. Manufacturing instructions specify the sequence of operations, tools required, and inspection methods to ensure quality control. CAD software generates these documents directly from the 3D models, streamlining the transition from design to production. Ensuring that these documents are accurate and up-to-date is crucial for reducing errors during manufacturing and improving the production timeline.